Hello everyone, welcome to the channel. In this video, we are going to review a strategy for trigonometric integrals involving sines and cosines. So we'll go ahead and jump right into this. So the first thing you need to look at is whether or not what the powers are for the sines and the cosines. Sorry, this is bothering me a little bit. So if your cosine power is odd, right? So if your cosine power is odd, so this means it is of the form n equals 2k plus 1 or 2k minus 1, but 2k plus 1, then what you want to do is you want to pull out a factor of cosine, which drops it down to even, and then you want to express that cosine in terms of sine, right? So this is what this is going to look like. So you have the integral of sine m x cosine n x dx, and we're going to rewrite this n as 2k plus 1. So that's going to be the integral of sine m x cosine 2k. Well, I'm going to write it on the outside since that's a bigger exponent to write. So this is cosine x 2k plus 1 dx. So you want to save one factor of cosine, because remember, when you add exponents, it's because you're multiplying their bases, right? So this is going to become sine m x cosine x 2k times cosine x to the 1 power, right? dx. Now, what you do here is you want to choose u is equal to sine, okay? So when you do this, what you end up with is what you end up with is u equals sine, right? Sine x du is equal to cosine x dx. And then this term right here, you're going to break that into a cosine squared of x to the kth power, right? Because when you're multiplying these exponents, you can move them. You'll see. So you have sine mx, and then it's going to be a cosine squared x to the kth power cosine x dx. Now we're going to use this u substitution and this du. So this du right here, we can make that sub. Well, first, before we get there, let's do this. Now we're going to rewrite this cosine in terms of sine. So we have sine m x times 1 minus cosine squared. I'm sorry, 1 minus sine squared. Got ahead of myself. 1 minus sine squared x to the k power cosine x dx. Now we're ready to make this u sub. So then we say u is equal to sine x and du is equal to cosine x dx. So then we have u to the m power times 1 minus u squared all to the k power du. And then from there, you can go forward with solving this integral like you would with any other integral of this form. And then when you're done, you just convert back for your u is equal to sine of x, right? So this is going to be the first one, the first little strategy. There's going to be 3 of them here. The second one is going to be if sine is odd. So if sine is an odd power. So that means m is equal to 2k plus 1. And it's going to be the same thing we did with cosine, except we're going to swap what our u's are, right? So we have sine m x cosine n x dx. And then if m is equal to 2k plus 1, then we have sine of x 2k plus 1 cosine n of x dx. And then we're going to separate this sine out into a factor of sine to the 2k power times sine. And we're going to move that sine over to the dx because this is all multiplication and we can move things through here. So we're going to end up with sine of x to the 2k times cosine n x times sine x dx. And then again, as before, I'm going through this fast because we've already seen all of this at the previous steps. So this is a sine squared to the k power. So this is going to turn into 1 minus cosine squared of x to the k power times cosine n x sine of x dx. So we are going to let u equals cosine here. So for u equals cosine x, du is equal to negative sine x dx. So negative du is equal to sine x dx. So now we have sine x dx right here. So we're going to replace this with a negative du. So I'm just going to put the du in and put a negative out in front of this integral. And then I'm going to replace all of our cosines with a u and then give them the appropriate powers. So we're going to have negative 1 minus u squared all to the k times u to the n du. And then you go forward with solving this the same way you would. Basically, this is going to be, you're going to expand out. So it's the same way with this one right here, right? So what you are likely going to end up doing is expanding this out using FOIL, this 1 minus u squared term in both of these, and then multiply that u to the n in there, and then use your antiderivative property for doing the power rule. And then once you evaluate that integral, you're going to go back and plug in your u, okay? So the third one, the third property or strategy or whatever, is going to be if both sine and cosine are even, right? So this is going to be if cosine and sine are, well, have even powers, right? So that's essentially going to be where both m, I'll say m equals 2k plus 1, and I'll let n equals 2l. Trying to think of a variable here. 2q plus 1, right? No, I'm sorry. Those are odd. So it's just 2k and 2q, right? M equals 2k, n equals 2q, right? So if they both have even powers, then what you want to do is you want to take advantage of the power reduction formula. So you have sine squared of x is equal to 1/2 times 1 minus cosine 2 theta, or 2x, I'm sorry, we're using x here. Okay? And then you also have cosine squared of x is equal to 1/2 times 1 plus cosine of 2x. And so if you have 2 to the k, then this whole thing is going to be to the kth power. And this whole thing, so this will be k and this will be q. This whole thing here will be to the qth power. And then you expand those out. And then if you have another term in here, let's say you have like a cosine squared 2x, well, you just do the same thing with that, and that's going to be 1/2 times, now this isn't taking into consideration this, so if you've already done this part, then you're going to have another factor of 1/2 in here. But let's just say that we started with this, right? So that means this is going to be 1/2 times 1 plus cosine 4x. So if you're not familiar with these power reduction formulas, I highly suggest you go look at them. And really, all of your trig identities, if you're in Cal 2 and you're doing trigonometric integrals, you're likely doing trigonometric substitution. And you really need to have a good fundamental grasp of how to write cosine of 2 theta, sine of 2 theta, your power reduction formulas, and your basic Pythagorean identities when it comes to these things, to the trigonometric integrals. So one more thing is, you also will likely want to be familiar with sine of 2x is equal to 2 sine x cosine x. So that means that if you have something like sine x cosine x in your integral, then you can replace this with a 1/2 sine 2x, right? Because if we work that out real quick, you get 1/2 sine 2x is equal to 1/2 times 2 sine x cosine x, which is equal to sine x cosine x. And then the other one you'll likely, you might want to know and keep on hand in your brain is cosine 2x is going to be equal to cosine squared of x minus sine squared of x. So these are some helpful properties, identities that you'll want to know, along with this power reduction stuff. So just remember that if your cosine power is odd, so it's 2k plus 1, then what you want to do is you want to separate out one of those cosine terms. You want to change that cosine, which is then going to be, you're going to have an odd cosine and an even cosine term. So you want to rewrite that even one as cosine squared to a power. It's going to remain even. And then inside, you're going to get something like this, where you have a cosine squared, which you can replace with 1 minus sine squared. And then you let your u equal sine. And when you do this and you find your du, you end up back subbing in all of your sines for u. And then you're left with just a regular power. Let's call it a power integral. And then if your sine is an odd power, you're just going to do the same thing but with sine. You're going to separate out a sine, you're going to rewrite that even sine, that sine to an even power as a 1 minus cosine squared. You're going to let u equal your cosine, and then from there you can do your u substitution. And lastly, if they're both even powers, then you'll want to take advantage of the power reduction formulas and go from there. And I would recommend, keeping these double angle formulas in the back of your head as well, because when you see things like this, sometimes it's a lot easier to do an integral if it's of, let's say, this form. But if you try to just start doing it with this form and you think, oh, integration by parts, well, this is going to be repeating, right? Because one of these terms does not go down to a constant and eventually integrate out to 0, right? So you want to be able to convert something like this right here to something like this, where you can use a u sub for your argument of your trig function, right? That's how that becomes helpful. So I hope this video was helpful. I'm going to put up another video for strategies using for tangent and secant, and then after that I will work some more problems using both strategies, or using the strategies for sine, cosine, tangent, and secant, so you all can see how they play out in a real world example. Okay, so if you have any questions, comments, concerns, feel free to let me know. Again, if you have any requests, go ahead and send me an email at the email provided in the comment or the description, and I will try to get that problem worked out and put in a video as quickly as I can. All right, thank you. Have a good day.